Here's the hardest type of problem. You're given a function. Maybe the function is not that complicated. 3x squared y cubed plus maybe e to the xy. But the region you want to integrate this over is complicated. We probably won't be able to do this integral by hand, but let's integrate this over disk centered at the origin of radius 2. Once again, our D is going to be the set of points in the plane such that x squared plus y squared is less than or equal to 4. Our goal is to find the double integral of this function over D. There's how you write it in the abstract. Graphically, if the graph were above the xy plane, if it were a surface above the xy plane, you're trying to find the volume under that surface. If the graph goes both above and below the xy plane, then it's a signed area. When the graph is below the xy plane, you're trying to find the volume above it, and it counts negatively toward the integral. This function, I did make it so that the graph probably does go negative, perhaps, because of the y cubed. When y is negative, that'll be negative. I mean, maybe this will be compensated by the e to the xy to not be negative. I'm not sure. Let's just see. I made it hard enough that probably it's not really possible to do this integral by hand, but I'm just illustrating concepts here. Setting up the integral in many situations is more important than actually doing it. I mean, you want to be able to do it as well, but the more important skill is setting it up. So we could still set it up here and see if Mathematica can do it for us. So there's the function. Let's first see what its plot looks like. Plot 3D. There's what the graph looks like. It does go below the xy plane. See 0 right there? So there's no guarantee the integral is positive. It could be negative. Looks like it goes up high enough and down low enough that we're not seeing the full graph. It's getting cut off. I could try to change the plot range in the vertical direction to change that. We're almost seeing the whole graph now. How you set up the integral. And if this function did represent a probability density function like the application from Wednesday, it wouldn't because it goes negative. But if it were always above the xy plane, whatever the value of the integral is, pretend it's 17, then 1/17 times the function would be a probability density function to make the integral 1. But you don't want to allow probability density functions to go negative. And on Monday, we will talk some about mass density functions and integrals that give you mass and centers of mass. You don't want those functions to go negative either, just like with probability density functions. But right now, emphasis is on setting up the integral, either using dA equals dx dy or dA equals dy dx. And the most typical way to do it is actually the second. Because most typically, not always, but most typically, you think about your region here, D, as being between the graphs of two functions of x. Y goes between two functions of x. And so if the inner integral is with respect to y, you're integrating between two functions of x, the y is going to go away, is the idea. So when you think about your region as being between the graphs of two functions of x, you want to use this form of dA. If you were thinking about it as being between two functions of y, which you could, here, this is a symmetric kind of picture, you could think about it as being between these two sideways graphs as functions of y. X goes between those two functions of y. Then you'd want to use that. But let's think about it this way. How would you set it up? This is the hardest skill, the most important skill. The outer integral is going to be with respect to x. You want the limits of integration to be constants. X goes over the whole region between -2 and 2. That's the outer integral. We're going to use parentheses again for emphasis, though you don't have to use parentheses when you do problems. There's an inner integral and an outer integral. That's why I'm using the parentheses, is to emphasize that. There's the function, the inner integrals with respect to y, outer integrals with respect to x. All that's left is to figure out the limits of integration for the inner integral. That's the hardest thing. For any value of x between -2 and 2, y varies between two functions of x. A lower function and an upper function. The equation of the upper one, the upper semicircle, solve for y, is square root of 4 minus x squared. The equation of the lower semicircle is y equals negative square root of 4 minus x squared. Those become the limits of integration for the inner integral. Technically, doing the inner integral by hand is not difficult. Let's go ahead and do that one by hand. The outer integral, because of these square roots, might be too hard. But let's see how the inner integral goes. Keep the outer integral as is. Do the inner integral with respect to y. Treat the x as constant. The first term you see is 3x squared y cubed. Treat the 3x squared as a constant. I got to raise y's power by 1 to 4 and divide by the same number, 4, giving me 3/4 x squared y to the 4th. This one's a little trickier. Once again, treat the x as a constant. Pretend it's a 5 or something. If this were e to the 5y and I were integrating that with respect to y, I get 1/5 e to the 5y. By analogy here, you would get 1 over x e to the xy. Y goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared. When you plug those things in for y, the result will depend on x. And you're going to integrate with respect to x, but it's probably going to be too hard. You're even going to have a square root in that power of e. We could still numerically approximate it, though. I mean, it's kind of a mess. Let's see, plug in the square root. You'll get 3/4 x squared y to the 4th. We'll make this thing b to the 2nd power because it's a square root. Actually, because of raising to the 4th power there, when we plug in the negative square root, we're going to be subtracting that term. We are going to get some cancellation. Plug in the positive square root there for y, you'll get e to the x square root of 4 minus x squared over x. I'm seeing something I don't like here. That is going to maybe make this not doable. I picked an example that's maybe not doable. Dividing by x there, we'd be dividing by 0 at x equals 0. Improper integral. Start over. Okay. Plug in the other one. Including with the negative sign, if I raise it to an even power, the negative is going to go away. Ultimately, this will cancel with that. Plug it in there. Get e to the negative x squared of 4 minus x squared. Interesting looking integral. And it's possible it may even be related to the hyperbolic cosine function because of adding opposite powers of e there. I don't know. Probably this integral is going to diverge. I can't imagine you could do it by hand, even if it does converge. You feel like you could do it? You think I can do it? Let's even just see if it has an antiderivative. That's a simple function. Probably when I enter this, nothing's going to happen. Like, or give up. Okay, that's Mathematica saying I give up. Okay. And you can try to do n integrate to do the integral from -2 to 2, but probably it's going to spin its wheels there too, because it's an improper integral that probably doesn't converge. Yeah. Being considered, okay. Well, may actually, it says it down here, it says it may actually be divergent. I mean, we could try integrating it from 0 to 2 as well. Okay, it's giving a number. I have no idea if that's right or not. My guess is it's wrong, because probably the integral diverges and it's trying to do it without knowing that. And integrate is just it's quote unquote dumb command, because it's just doing numerical integration without thinking about convergence or not. So probably I picked a bad example. Probably it diverges. Although, I mean, the graph's not too strange. I mean, the volume of that should exist, right? Is it going off to infinity there? Probably not. All right, yeah, it shouldn't be. I mean, so technically speaking, it's a continuous function of the domain. So technically speaking, the integral should exist. The volume should exist. I just don't trust that it's this or double that or whatever. It's possible because symmetry, it's 0 in the end. Is it really truly symmetric? I mean, maybe not completely symmetric. I'm not sure. Yeah.
It showed on the graph where it looks like it's diverging the same way in positive and negative directions.
Okay. So the answer ends up being 0 or something. Okay. So in the end, the answer may be 0. Anyway, the important thing, let me just do equals ... The important thing is setting this thing up. If you're going to do it with respect to the other order, the outer integrals with respect to y still goes from -2 to 2. Look at the picture. Symmetry in the picture. That doesn't always happen. You don't always have symmetry. X goes between two functions of y, negative square root of 4 minus y squared, the positive square root of 4 minus y squared. The function dx dy.